Thanks, Pasha, and thank you all for coming. Our first speaker for today is Maxim Kontsevich from IHS. And so let me just tell that, as far as I remember, he attended Gelfand seminar since he was 14, I think.
15. 15.
Well, all right, so close. Okay, so he will talk about stability and Fukaya categories.
Okay, thank you. Okay, thank you. So I want to say that mathematics is an art to give precise and true statements. And I'm afraid from some point my talk will be very non-mathematical, so please don't be afraid if you get lost. So I want to speak about stability, but first I would just want to say that in algebra and in algebraic geometry, we have some similar looking modally problems. Some modally problems. And what is modally problem, typical modally problem in algebra? Suppose we are given a quiver, finite quiver, some collection of loops, arrows, something like this, quiver Q. And we are interested in classifying or describes this set of equivalence classes of finite dimensional representation of queries. So it means that for each vertex we get a vector space, let's say over complex numbers over a given dimension. And for each arrow we get a linear map. And I want to study isomorphism classes of such guys. And so we get representations of quiver are the same as modules over some algebra, over it's called path algebra over quiver, which are finite dimensional or as vector spaces. Okay, and in algebraic geometry, usually we have some, let's say, projective variety. And we're interested in, let's say, vector bundles or coherent sheaves. Let's write coherent sheaves on X. One can remove the constraint that variety is projective and say that instead of coherent sheaves, consider coherent sheaves with compact support. It's analog of this condition that dimension is finite. And modular space of such things also form some whatever derived stacks of finite type. And in both cases, what we have, we get certain abelian category. A, which is coherent sheaves or representation of quiver, responsible, and we study what are modular problems. It's modular spaces of objects. Of this category. That's what we're interested in. Gradually, it became clear in those kind of questions that the abelian category is not a right kind of framework. There is something hidden behind it. It's some triangulated category. Better replace A by a triangulated category. What is triangulated category? So the basic example, it's not necessary, but basic example is bounded derived category of the abelian category, which means that you consider finite complexes of objects of finite lengths, and model a certain homotopy, you get derived category. So in particular, for each object, you get individual cohomology, which will be object of this category. And why it's good? One of the reasons why it's better to go from abelian categories to triangulated ones is that often one have different triangulated categories, abelian categories, such that corresponding derived categories B stay for bounded, finite complexes are equivalent. It can happen for algebras, for varieties, or even one can make examples when derived category of coherency of some variety is equivalent to derived category of representation of some quiver. So it's really makes the 6 undistinguishable. And I think one of the earliest examples of such situation when different abelian categories have the same derived categories is called example of so-called Gelfand-Ponomarev reflection functors, which identify two different derived categories. Imagine, so it's in a situation of quivers. Imagine that you have a quiver and you have a vertex, which you denote by V0, which is a source. So all arrows emanates from this vertex and nothing ends there. And then you get it goes to arrows go to some vertices, say different one, V1, V2, Vk, and there are some other vertices which I don't denote. And when you consider representation of the quiver, you get a vector space at each vertex, and I get linear map. And then we have a map from EV0 to the direct sum around to K EVI. What can happen with this map? Typically, if you just take big dimension of the space at of this, almost the same size and pick maps at random, this should be immersion. But sometimes it's not immersion. And if the kernel of this map, that's called some alpha 1, alpha k, so it's sum over alpha I, is not 0, then one can split this object of category representation into simple things. One can split in vector space supported in just kernel of this map put in degree 0. You split vector space as sum of kernel and some complementary space. And then the map everywhere will be 0. So I get put 0 in any other thing, plus another representation such that sum over alpha I has no kernel. It's an inclusion. And then, so let's assume that we don't have any kernel. Then we can essentially identify EV0 with a subspace. And when you get a subspace, you can make a quotient space. So let's denote by E prime V0 will be quotient. And then each of these guy maps here, and you get epimorph. Then you get the following thing. You get collection of maps going in opposite direction. You reflect all arrows at vertex V0, so it will begin a sync. And you get the same picture everywhere. So essentially, you identify moduli problems in for one quiver in another. But here we get some small exceptions. We make the small assumptions that kernel is non-zero. So in abelian categories, the moduli spaces are not exactly the same because of this small difference. And in triangulated categories, when replaced by complexes, everything became perfect, so the derived category will be equivalent. Roughly speaking, you replace this quotient in general by a two-step complex. In degree -1, you put EV0. In degree k, you take sum from 1 to k to EVI, and you get this our map somewhere alpha I as a differential. And if it's inclusion, then I can replace by quotient. So I get it EV0 prime is this complex. Okay, yeah, so that's short introduction why triangulated categories are better than abelian one. Yeah, but okay, so we get abelian category. Now let's return to this general question. We get abelian category, and we want to classify objects, but to get good modular space, one should apply some kind of geometric invariance theory. Sorry?
Could you please repeat why this won't happen in triangulated categories?
It's a simple exercise. In triangulated category, if you define such things, you get equivalence of categories of representations. Okay, so apply some kind of Mumford theory of quotients. One should apply to Mumford theory of quotient, and then one needs something like stability. That's the origin of what I'm going to talk about. And for quivers, one kind of measure stability by some kind of slope of representation. And slope is something like this. You take sum of all vertices of your quiver. You get certain number. Lambda v will be real numbers or rational numbers multiplied by dimension of representation at point V, and divide by total sum of dimensions. And you're interested in something like representations with certain slope which don't contain sub-representation with a larger or smaller slope. And similarly, for vector bundles on curve, you
where do you take lambdas from?
it's something will depend on lambda. You choose some lambda, and then you start to play some game with stability. And for example, for variety, you define if x is a curve, it will be now coherent shift, so vector bundle. You divide degree by rank and uses this kind of tool to treat stability. Okay, so I think I can remove this example. So now I'm ready to give a definition, assuming that you know what is triangulated category. So it's by Tom Bridgeland. For given triangulated category, which I denote by C, a stability condition on C is consists of two pieces of data.
On the left,
Yeah.
this work doesn't involve the maps.
No, it doesn't. But here it's also kind of topological. It doesn't involve holomorphic structure. So stability condition consists of two parts. One is called Z, or because of physics origin, it's called central charge. Z is a map from K group, K0 of my triangulated category, like abelian category. Triangulated category has K0 group. It's a abelian group. And this is a map to two copies of R, which is in a sense related to the thing, which is convenient to identify with the complex numbers. And the second piece of data is a collection of sorry, just clean, of full subcategories. So it means that just collection of isomorphism classes of objects just some collection of object classes under isomorphism and satisfying following axioms. First, if you get object in one of these classes, then it gives the class in case theory. Then you can apply Z, you get a complex number. And this complex number should be non-zero and have argument exactly equal to theta. So it's, yeah, that's what I've written here. Second constraint is that if you get an object and shifted by one, for example, if you consider complex, you shift grading by one in this complex. It's one part of structure in triangulated category. This will be a SS state for semi-stable. It will be semi-stable object with argument shifted by pi. Then this number will, class in case zero goes to opposite, and argument will change it by pi.
Are we discussing some known stuff or in-use stuff?
It's Bridgeland definition. Okay, I don't know. It's known stuff for 10 years, 15 years. Okay. Yeah. No, it's not. Okay. And the third is the main axiom that any object, so there are such kind of basic building blocks, and the third axiom said that any object canonically decomposes in elementary pieces. For any object F, there exists unique some number n, kind of length, and the sequence of maps. Maybe just exchange addresses. And a sequence of maps from one object to another, so on. And sequence of numbers. Such that, okay. For any morphism in triangulated category, you can make a new object, something like quotient or kernel of the map in usual abelian category, denoted as cone, and that should be semi-stable with certain slopes, and slopes should be strictly decreasing. Okay, that's all axiomatics. And it's very beautiful notions. The stability condition, one can identify with kind of amalgam of two more or less known previous notions. First, it's you get a bounded T structure. Bounded T structure means that you can speak about if you think about complexes supported in certain degrees, let's say biggest and certain number. In particular, you can speak about complex supported degree 0. And in degree 0, you get something called heart of this T structure. And heart is always abelian category. Yeah, so it's, in general, if you get bounded T structure, C is not the same as bounded derived category. It's maybe some small deformation of it, but it's close to it. So if so you get kind of link between abelian categories in triangulated categories, abelian category, you get abelian category. And then from abelian category, you get, we can restrict the central charge to K group of the abelian category. But for abelian category in K group has a positive submonoid classes represented by actual object, not formal differences. And these things should map to what I denote, it's kind of upper half plane. It's a set of complex numbers, which is either in a strictly upper half plane, or Z belongs to R non-positive. Yeah, so you get kind of this subset of complex numbers, and such that if Z of E is equal to 0, then equal to 0, so all objects with central charge mapping to 0 are 0 object, and then one define semi-stable objects. It is or maybe theta stable. Non-zero object we call theta stable if argument of Z of eta is number theta, which in this case should be from 0 to pi included. And for any E prime contains in 0 which non-equal argument V prime is strictly less than theta. So you get some kind of basic stable objects. And then any object should have a filtration. We're going to get here inclusions with increasing slopes. Yeah, so it's
Maxim, so your equivalent sign is it equivalent to both 1 or 2 or 1?
No. This stability structure, which is given by Z and something in triangulated category, is the same as bounded T structure and something on abelian category. Yeah? Yeah, it's just equivalency. Okay, yeah. Maybe 3. Okay. Yes, it strengthens out some properties. Sorry?
To get a real equivalence, don't you also need to postulate this?
Yeah, I should postulate similar axioms on abelian category. Okay. So again, what's the basic example? Yeah, it looks something complicated. But suppose we consider category of finite dimensional representation of quiver, and we get usual T structure. So the heart will be just CQ models, it will be abelian category, and then defined and then choose complex numbers ZV in H minus 0 arbitrary. For each vertex, you choose a non-zero number in this set. Then we get a map from K0 to whatever C, abelian category, maps to a set of integers to power the set of vertices of my quiver. And then it maps to C. Essentially, if we get representation, we go to sum over this ZV multiplied by dimension of EV. You choose this number arbitrary, and then this extra condition, which exists in such thing, it's completely obvious because in any object you choose a non-trivial subobject with a maximal slope. Make a quotient and repeat the procedure. And because dimension is finite, you stop at some point. Yeah, so that's completely free because this abelian category is called Artinian. It has finite length. Any central charge will sufficient. Now I'll just go to the most interesting example, simplest example. So suppose a quiver is Kronecker quiver is 2 vertices and 2 arrows. So we get 2 vector space and 2 linear maps from one to another. And I want to make a list of all stable objects. Not yeah. In order to get stability, I explained first you choose two numbers. So if you consider the first case, that argument of, let's say, Z2 is bigger than argument of Z1. Then the list of stable objects and their central charges, there are only two of them. One, you get 0 maps twice by 0 maps to C, and another C maps twice by 0 maps to 0. You get just two objects. From which you can, by extension, build any object of your category. And there is a second case when argument it's opposite, but let's make a choice. Z1 is equal to -1, and Z2 is equal to -1 plus I. And then we'll get the following picture. So we get 0 in my upper half plane, which is not represented by any stable object. But then we get actual object in point -1, which correspond to C maps twice to 0. Then we get something at -1 plus I, which will be C square maps twice to C, but by different maps, and so on. Then we get something here, which will be just symmetric. And then you get whole, and here you get representations in of when you get just one C here, you get A multiplication by two complex numbers, A and B, where A and B is a non-zero pair, so should get a ratio which is point on projective line. So you see that moduli space of objects, and this will be all simple or the stable object in this situation. So the list of stable objects will be the following. It's here parameterized by CP1, we then get point, 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 point. Here it's also get point. So you get this nice diagram. Representations two one-dimensional spaces and two I, yeah. Oh, yeah, I. Okay. And you get nothing else. Okay. Then you can try to make a different thing in algebraic geometry. Now consider X will be projective curve. Actually, projective, yeah, smooth projective curve. And so the category will be dB of coherent sheaves. Of this curve, abelian category will be coherent sheaves. And what will be my central charge? Will be minus degree of my coherent sheaf plus I times rank. Okay. And now specialize it to the case when X is CP1. And then one get a different picture. Namely, we will know stable object with central charge 0, but in degree -1, one get CP1. And then here we get point, 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 point. Yeah, what are corresponding sheaves? Here the corresponding sheaves is O0, then O-1, and so on, O1, all line bundles. And here will be O of the ideal of a point. Kind of skyscraper ship at some point of CP1. Yeah, so you see that you get CP1 an infinite sequence of points. But in triangulated category, one should reflect the things because you get shifts by one. So one get kind of symmetric reflection of this picture and make the symmetric reflection of this picture here. And you get the same thing. You should just rotate by 90 degrees. And the fact that this bounded derived category of representation of this quiver is bounded derived category of representation of coherent shifts on P1. And what happens with stability conditions? You just multiply this Z by constant. If you multiply Z by constant, you make a new stability condition. Yeah, so this identifies these two thing. Yeah, actually, this ability to multiply by constant, it's very remarkable. One get not one T-structure, not one abelian category, but whole continuous families of abelian categories. And they're completely new abelian categories which people never met before. So it's even for... yes, you consider objects. I will go in a second. What is it? I have two half series. And after reflecting, I get two infinite series, two-sided series.
So the negative pole are not on the same line as positive pole.
No, I have all n, where n I in degree I minus n, where n is integer.
Here they were on two lines.
No, here it's one line.
Yes, but upstairs it was two lines.
Yeah, but now in triangulated categories, I should also add minus of my things. I make completely symmetric picture. And after making picture symmetric, I'll have the same way. Okay. Yeah, so so any stability any stability conditions and any real number gives us three abelian categories. What will the abelian categories? I will just write a notation, and then you'll understand what is it. It will be C theta, C of theta plus pi, and C of theta plus pi. Here I write different subsets of real numbers, and by this thing I mean this all objects in my big triangulated categories such that all constituents in this decomposition have arguments exactly in these intervals. And all these guys are abelian categories, and one of them, I think, this guy corresponds to this upper half plane T-structure, heart of the upper half plane T-structure. Yeah, so this notion of T-structure is what is the main beauty of the definition is the following. It's kind of a very basic result. Let's make some technical assumptions which holds in all real-life situations, that there exists some map from K group of my category to some finite rank lattice. And Z is composition of map from this lattice. And I can assume this apomorphism. So I suppose I fix this. I consider central charge with factors to some quotient, which means that I calculate some kind of like Chern numbers of my coherent shifts or dimensions. And also, I want some kind of support property, which means that if you consider all semi-stable objects with all possible slopes, then the norm of this vector in the n, this would take subnorm, whatever, is is less than capital O of the absolute value of Z of E. Roughly speaking, it means that, for example, if n equal to 3, you imagine you get maps from Z3 to C, some kind of three-dimensional lattice maps to a plane. And it means that all interesting objects are, semi-stable objects are outside of these two cones, which will be near the kernel of the projector. Yeah, so it's some reasonable condition with this thing. And then consider space of stability conditions of my category. Again, going through this map class to some Chern class to some Zn. Maps to Cn. Locally, you go from Z, you go to and collection of category. Forget this, just go to the central map, central charge Z. You forget all these categories. You have maps to Cn. And the claim is locally a homomorphism. In some natural topology. So in particular, for each stability condition, you can move it a little bit. And then you see that this guy is a complex manifold. Yeah, and then people kind of were enchanted. You get complex manifold from any triangulated category from nothing. And this complex manifold, it's locally a cone, open cone in a vector space. But actually, this beauty is actually deceiving. It's misleading beauty, and that is not why we should be interested in stability conditions. Yeah, so people want to see that you get some beautiful complex manifold out of algebra problem. But what I explain that one should, what it's good for, it's something else. Yeah, so what is morally stability condition? What kind of objects in usual mathematics which we can consider as parallel to stability conditions? Stability condition is similar to choice of kind of ample or Keller class in algebraic geometry. It's kind of extension of Keller class to this derived world. Under some reasonable assumption, when consider coarse, what one can see, if you get under some assumption, some assumptions, one can form, if you get category with stability, then for any class in this, suppose we get also this map in Zn, in some lattice, for any class, one can get, and one get moduli space, coarse moduli space of objects in class gamma, which should be kind of polystable objects. In corresponding class in K-series, so like dimension of representational quiver. And polystables are, in this language, I forgot to have a billion category description, which I already removed. It's direct sums of stable objects, not. And this is a scheme of algebraic space under reasonable assumption of finite type, and then it will carry natural Keller class. This follows from axiomatics. And one can write the degree of in cohomology, in second cohomology, yeah. Yeah, if you get a curve, let's say curve X maps to this coarse moduli space, one can lift it to actual stack, one get a family of objects parameterized by curve. It will be projective curves. And what will be degree of this curve, integral of the Keller class of this curve? You consider a kind of R gamma of my curve of this class. You get another object of my triangulated category. One can say it's some adjoint functor or whatever. And one can show that take z of this guy and take exponent minus e theta and take minus imaginary part of this guy, and this is bigger than 0. It will be volume with respect to Keller class. And in some realistic, again, situation of quivers, one can actually produce certain additional data, like choice of Keller form in non-commutative sense, which produce Keller metrics on all the spaces. Yeah, so you get a lot of Keller varieties, which are not necessarily projectives, they are quasi-projective, because it's, I don't say that it's the integral of any compact curve is positive, but I don't think. Yeah, so you get. So what you get at the end of the day, you consider interesting gamma when you get non-trivial moduli spaces. By this property, support property, you get a discrete subset in complex numbers. There will be only finitely many central charges on a given distance, and for each point on this discrete subset, you get a quasi-projective variety. Yeah, so it will be a picture of your category, so a huge countable correction of quasi-projective varieties. And which change somehow if you move parameter of stability according to this result of Brigian that you can move it. Yeah, so it's very hard to construct stability conditions. So what we expect from string theory is that for categories equal boundary derived shifts on some coherent shifts on some, let's say, smooth projective variety, should we really expect any stability at all? It's not clear. But at least what string theory suggests that one should get a family of stability conditions, maybe for Calabi varieties, depending on kind of Planck constant, which is a very small number. And stability condition will be integral over Chern class, something which I will not speak about. It's called gamma class. It's something like square root of Todd class, but not exactly. And then you multiply by exponent h minus 1, maybe minus first Chern class of, let's say, ample line bundle denoted by O1 divided by 2 pi I. Now, it will be approximate. And these structures which you get, hard is not coherent shifts at all in the limit. It will be what's called perverse coherent shifts. Something like functions on some variety of certain dimension k, you shift by integer part of k over 2. It's more perverse coherent shifts. So one gets kind of very different intuition. So, and in real life, I think the best result now is by Brigian and Maciucci. They constructed such things for three-dimensional abelian varieties. So there is nothing known in, it was very hard to go to dimension 3. Dimension 1 is easy because it's very close to quiver, and this perverse coherent shifts are the same as coherent shifts. But in dimension 2, it's much harder work. In dimension 3, it's very hard work, and it seems to be close to impossible in higher dimensions. One needs some kind of generalization of Bogomolov-Miyaoka inequalities, and so it's a very hard analysis. Yeah. So that's all this. That's a picture, and what I want to say is that one shouldn't really deceived by this beauty. One should look for other things for the stability conditions. First of all, what they could be good for in kind of very general framework, because they kind of organize my category in some nice finite dimensional pieces. It's good for counting. If it's someday we want to introduce some kind of L function of triangulated category defined of integers, that will be through these stability conditions. Like usual L functions looks that we count objects on arithmetic scheme supported only at zero-dimensional part, which will be the objects close to zero in the 6. But it will be only leading term kind of, this L function will be a part of much larger picture. Yeah, but it's kind of daydreaming, and will speak about more reasonable daydreaming, where all this came from. And this another thing, it came from string theory, or more precisely, conformal field theory, and it will lead to some very vague conjectures. I will give a couple of conjectures towards the end of my talk. So the origin of all this, it was a work by Mike Douglas, who studied D-branes, which are boundary condition conformal field theory in supersymmetric conformal field theory, and how they start to disappear if you change parameters of conformal field theory. So he gets some kind of nice picture, and these D-branes were close to whatever stable holomorphic bundles. And Bridgent extracted from his scenario described by Douglas this definition, his definition. I have to admit that I really have no, I don't think there's any, up to now, satisfactory explanation why Bridgent axiomatics holds, even if we believe in all physics if you want. That's some partial explanation exists, but general thinks it's really kind of leap. So it's not clear why it's really one corresponds to another. But it looks nice in examples. And what actually physics suggests. So physics suggests is the following. You consider modular space of n equal to 2 superconformal field series with some given central charge. And up to gain some small technical details, it looks like a product of two modular spaces of mirror Calabi-Yau manifolds. Calabi-Yau varieties with trivial canonical class of the same dimension. So I get product of two modular space, and then one should get two topological twists, and one should get two triangulated categories, each with stability condition. And one category depends, as an abstract category, depends on point on MA, and stability condition depends on point on MB, and vice versa. So you get such things. But now, if you count, maybe, if you look on how many parameters, what the dimension of this modular space, they map to the space of stability conditions by linear maps, and then you get something strange. So the space of physical stabilities sits in the space of stabilities of my category, whatever, it's a coherent sheaves on some one variety, something like this. And it has, typically it has smaller dimensions than the right-hand side. It's not open subset. It's not an open subset what you get from physics, but you get some holomorphic transcendental column given by period mappings. And then by Bridgent theorem we get some kind of neighborhood, but these are not natural objects from point of view of physics. So it means that some stability conditions are better than another. I have really no idea what is it, but again, if I look on mirror symmetry, it implies that one should, that it's really fundamental question to find the definition of physical stability. So So let me write this kind of conjecture in not very mathematical sense because it's not, really, it's kind of in normal language. Conjecture is that there exists an intrinsic algebraic definition of a physical stability condition on, let's say, triangulated Calabi-Yau category. It's first things to that there exists some kind of pure algebraic definition, not using anything from physics. And second will be kind of mirror symmetry category plus this nice physical stability over complex numbers should correspond by some mysterious procedure to another category over complex numbers plus physical stability. Yeah, so it will be some transcendental construction going from one triangulated category and some unknown constraints on stability to another triangulated category. And moreover, one should expect each of them gives kind of mirror dual n equal to 2 supercontrolled field theory, which is huge collection of correlation functions for things on moduli space of curves and so on. Yeah. I really have no idea how to attack it, but I will give you some idea about some property which in some case could characterize this physical stability pure algebraically. Yeah, so that's so it will be kind of abstract mirror symmetry. But now go to geometric mirror symmetry and get actual varieties and so on. Then in geometric mirror symmetry, you get two mirror dual varieties, which actually families of varieties near cusps. Families of Calabi-Yau variety near cusps in their moduli space. So they depend on some parameters and close to be very, very degenerate. And then these categories, we know how they look like. One category should be bounded derived category of coherent shifts on variety. And another it will be equivalent to something called Foucault category of a dual variety, which depends on symplectic form, more precisely complex symplectic form. And homological mirror symmetry says that this object of mathematics are equivalent as triangulated category. And Foucault category, it's very heavy notion. There's still not good, no satisfactory exposition and even definition. But some objects are Lagrangian submanifolds in X with certain choices. Lagrangian submanifolds and morphisms are intersection points, and then one uses holomorphic disks in order to define something called A-infinity structure. So it's a long story. I will not go to this story at all. But it's something from which we know in some approximation what are objects. And in fact, this Foucault category, although its definition is not satisfactory, at the moment seems to be really the best way to think about triangulated categories in general. Basically, any triangulated category which you produce can, after some work, interpret as Foucault category, and it will be really right way to look on it, not as coherent shifts. And stability conditions are kind of clear geometrically on this Foucault side. So when consider Chern classes of coherent shifts on the left-hand side, they lie in kind of middle cohomology of X, which is isomorphic to sum over HP n minus P where n is a complex dimension of X dual, which is the same as Hn of X dual C. And class of Lagrangian manifold is this, maybe I can put Hn, is a class of Lagrangian manifold in H. And this, what all this conformal field theory suggests is that we know exactly what is the central charge coming from physical stability. On Calabi-Yau manifolds, you get a holomorphic volume form on each of them. I'll just consider holomorphic volume form on an X dual. And central charge of L will be integral over L of this holomorphic N0 form. OK, so that's a kind of answer which we can extract from physics. What are nice physical stability conditions in Foucault language. What are stable objects? Again, in some approximation we know it. It will be special Lagrangians. What is special Lagrangians? It's L, such that first it's Lagrangian, it means its scalar form vanishes restricted on N, L. And if you consider holomorphic volume form restricted to L, it makes sense to speak about argument of this thing, and because of the complex valued volume form on real manifold, and that should be constant theta. And this is nice elliptic system of equations. These things form finite dimensional modular space, and so on. And then in this language, one kind of can argue that Weisbrod axiomatics holds. So the main property. Main axiom, this kind of most transcendental thing, that any object you can deform the extension of semi-stable ones. And suppose you start with some Lagrangian manifold, which is not special. And what we can apply is some kind of mean curvature law. So the argument of omega n0 with respect to L is certain function from L to R. A priori, it's function defined modular by Z, but this additional constraint said that it's actually lifts to R. So you get a real valued function. And we can consider differential of this thing. It's a closed one form on L. And closed one form, it's you define a speed on which you deform your L because the normal direction is cotangent bundle. Yeah, so you get a way to deform your L. And then kind of by hand waving, one can convince yourself that something will decrease, the kind of volume will decrease. So it cannot go widely, cannot diverge. And then it should decompose to special Lagrangians. But these things can develop singularities. When it develops singularities, it will be locally looks like special Lagrangians, but different pieces will have different phases, and then you get small tubes next connecting them, and you get extensions, and you get this axiomatics of triangulated categories at the end of the day. Yeah, so it's a kind of big hope that it will go through some analysis. Yeah, okay. Now, and in these arguments, one can, if one can try again make hand waving, it's really not necessary this form to be holomorphic. It should be just closed, complex valued form. The main thing is omega n0 is taken to any real Lagrangian subspace in any tiny space. It's non-zero, and it's kind of open condition. You can wiggle around it. And now, but one thing one can try to guess is the following: why holomorphic forms are better than non-holomorphic forms? You can make a very big power of your manifold. And you can take many product of many copies of your form, yeah, kind of omega n 0 many, many times. Not kind of volume, some form omega, which is not necessarily holomorphic. You can make many, many copies. And if form fails to be holomorphic, then it looks that for very large big powers, this property will also disappear. And what it corresponds categorically, we go to big power tensor power of category, and we take big tensor power of central charge using multiplication of complex numbers. And it looks, again, hand-waving that if we fail, this form fails to be holomorphic, then for very big powers, it will be just false. So it will be a hypothetical algebraic description, maybe sufficient for a physical stability condition, but I have really no idea how to use it. Yeah, it's in this big plan. Yeah, so that's one thing. So we get a nice picture about holomorphic forms. But one can kind of mimic several things which you can think about conformal field theory and consider maybe not maximal degeneration, but intermediate degenerations, and get something more general. So eventually one can imagine the following picture. Suppose you have a variety is collapses is Keller variety, Keller Calabi-Yau, which maps to another Keller manifold which is not Calabi-Yau by some projection and with smaller dimension. And we want to describe what is Foucault category on X in terms of Y. And if you think a little bit, then let's assume it's fibration for simplicity. Then we get on Y the following things. On Y, get roughly a local system, or in general, constructible sheaf of triangulated categories, depending on point of Y. And then the stability condition will reduce the following. For each point Y, we get stability depending on Y from K group of the category to, just to make, to fiber of a canonical bundle at point Y of Y. So this determinant of cotangent bundle. It's not complex numbers, but one-dimensional space, but for stability conditions, it doesn't really matter. We can, yeah, so, and should we holomorphically depend on Y. Yeah, so one can make kind of more mixed things. Again, one can speak about special Lagrangians. It will be the following thing. It will be singular Lagrangian, consists of different pieces. And on each piece, you get object in your category. So one could be general object, and it will be semi-stable. If this guy will be semi-stable, and Li will be special Lagrange with respect to corresponding holomorphic form. Yeah, so get some kind of bizarre mixture of algebra and analysis. And in very simple cases, one can get spectral networks of Gayota-Murnetsky, which are now central object in kind of WKB theory for differential equations on curves for Hitchin systems. There are some kind of bizarre graphs drawn on complex curves. And that can interpret as a bundle of two-dimensional Calabi-Yau categories. And all these things gives nice geometric guys. OK, thank you.
So, dimension of physical stability is the last time dimension of
Yes.
stability.
Yeah.
So, in some ideal station, the right-hand side equals to the dimension of homology.
Yes.
Is the dimension of physical stability related to the dimension of second homology?
No. It's dimension of H0 plus H2. It's kind of it's terms on Hodge filtration if you interpret it in other way. Yeah. Okay. No. In fact, I see.
So I have two questions.
Yeah.
So I thought that at first the moduli space of stability conditions was supposed to be like some mathematical model of the stringy Kähler moduli space. But is your claim that physical stability...
No, it has a large dimension. Yeah, it's
great.
Yeah.
And my second question is, so this mean curvature flow gives you this gradient flow on the space of Lagrangians, things that want to be objects. Do you expect that for like special kinds of triangulated categories, you also have some sort of gradient-like flow then.
Yes, yes, yeah. Eventually, it should be some hard analysis mixed together with categories. Yeah.
Use the structure of whole algebra, and can it be helpful?
Whole algebra.
Whole algebra. So, because the first example that you
Yes, yes. If you get weavers, yeah. Yeah.
it's essentially a simple thing.
Yeah, no, for example, for three-dimensional Calabi-Yau categories, when you get stability, one can make this cohomological whole algebra, which we introduced with Soibelman, which is responsible for Donaldson Thomas invariance. But yeah, but for any counting, you need stability. That's another point.